What's up, Algebra 2? Hi! I missed you guys. I don't know how long it's been since you've seen me, but yeah. Okay, so we're starting something kind of newish. Still functions, but piecewise functions is what we're going to be starting today. So that's fun. So by the end of today, we're going to be able to define a piecewise function, give equations for piecewise functions, and graph piecewise functions if you're given an equation for them. Okay, so piecewise function. A piecewise function is like exactly what it sounds like. It's defined by pieces. Yay! Okay, so the graph on the right is an example of a piecewise function. As you can see, there's different chunks, right? So there's like a chunk on the left side of -2. There's a chunk of a graph in between -2 and 1 on the x-axis, and then there's a chunk after 1. Okay, and so you kind of want to think about it like neighbors with a fence in between them, right? So like you've got these two people and they don't really like each other, and so they don't want to share the fence. So the fence has to belong to the person whose property it's on, right? So you've got dude number 1 over here, and he's like really not a pleasant person. And then you've got dude number 2, we'll make her a dudette. Also kind of like meh, like to stick to myself. Okay, and then you've got, let's do number 3 is slightly happier because he has a mullet, and they each have their own property, right? So girl 1 lives in her world, right? Neighbor 1 lives in her world, and she lives in this world that is the function, whatever this little thing is here, okay? So she and dude 2 share a fence, right? And that's this one in the middle, and in between the two of them, right? And so you have to figure out, part of your job is to figure out who the fence belongs to. Who's allowed to get really, really close to the fence, but not actually like sit on top of it, and who actually can sit on top of the fence because they own it. So the girl in this case, right, because as you see here, there's a closed dot at -2, and that's on girl's side. Okay, she actually can sit on the fence, right? So that's her reign. She belongs to the fence and anything over from the fence, okay? And then you've got dude in the middle, and he can get super, super close to the fence. He can like even like peek through the fence, right? But he can't, and like creepily stare at his neighbor, but he can't actually sit on top of the fence, otherwise the girl's gonna get really mad at him. So he lives in this -2 to +1 range, right? But he can't actually live at -2, and he can't actually live at 1, right? Hence the open dots on both sides. So he doesn't actually have a fence, which is probably why he's really mad, because he doesn't actually, he doesn't get to sit on a fence, which is very sad. And then the last guy, if you can tell, right? Because this function, he actually has a closed dot, which means he can equal 1, means the fence belongs to him. And so therefore, this function lives on the side of the fence and on the fence that is +1 all the way to +infinity. Okay, so it's just like breaking up a function in a bunch of different like sections, and you have a different type of function in each section. So you just have to make sure that you like define your sections appropriately and define your functions appropriately, and that's it. Okay, so the question is, how do we actually write this function? And you know, functions we usually write as f of x equals, or g of x equals, or whatever, right? So we're going to call the entire function f of x. And I'm going to make it a really big f of x because, well, you'll see. Okay, so f of x equals, and usually it's something like 2x plus 1, right? But in this case, we have 3 different chunks, right? So you have to tell me the equation of each of the chunks, and you need to tell me where those chunks exist. So basically, define who the neighbor is and where their property lies. Okay, so you should get really good at drawing these like fancy little brackets, because we have function 1, function 2, and function 3, and then we want to say where those exist. So it kind of looks like the general format looks like this. Okay, so first chunk, girl, evil girl who belongs on the fence, right? She exists in the world that is -2 all the way down to -infinity. So if x is -infinity to -2, and remember, she belongs on the fence, she can sit on the fence, so she includes -2. Then we need to figure out what the equation of that actual function is. Like, what's the girl's name? Okay, so this function, if it were all by itself, would be the function y equals 1, right? So we would just say f of x equals 1, right? So it's kind of like f of x equals 1 is f of x equals 1. And so we're just saying that's the equation of the line when x is between -infinity and -2. Okay, next we have to define the next piece. So this was piece 1. Piece 2 is this little parabola looking thing, and this is in fact an exact parabola y equals x squared. So this will either be given to you or you'll have to kind of figure it out. But in this case, right, you can see 0, 0 is a point, 1, 1 is a point, -1, 1, and then -2, 4 is a point. So you can see that it's not stretched, it's not shifted, right? It's just your basic parent parabola. So the equation of the function is x squared, right? So normally I would say that's y equals x squared, and so therefore I have y equals x squared. It's just in a chunk. Okay. You also need to tell me where that exists, where the boundaries of that function's property, right? So this function only exists from -2 to 1. And because it cannot equal -2 and it cannot equal 1, it can't sit on either of the fences next to it. It's just less than signs, right? So we say we have the function x squared if x is between -2 and +1. No equal signs because it can't actually equal the boundaries. And last but not least is the last chunk of the function, right? The last dude with the mullet. And his function is a line, clearly. We need to figure out the equation of the line. So we need, what would the y-intercept be if it actually existed? Because as you can tell, it doesn't actually exist where the y-intercept is, but like if I were to extend this all the way down, you can see that the y-intercept would be -1. So the equation of this line is going to be y equals mx plus b, where b is the y-intercept, so y equals mx, minus 1. I'm running out of room here. But the thing is, we need to figure out our slope. So let's look at rise over run. We go up 2 and over 2, right? So 2 up 2 over 2. So our slope is 2 over 2, which is 1. So the equation of that particular line is y equals x minus 1. And so in my little function, I say x minus 1 is the equation, and then I need to make sure I define where is the boundary of that function, and it exists from positive 1 all the way to positive infinity. And this function is allowed to sit on the fence, which means it has an equal sign. So 1 to positive infinity. So this function creates this graph. Now if we want to go the other way, start with an equation and make a graph. There's kind of two ways I like to think about it. Method one is just graph it, or pick points and then like plot it, right? So pick values of x and then figure out which piece of the function it's on. So like plot points and make a table, but just make sure that you're using the right function for the x value, like not crossing over boundaries. The other option, and this is kind of what I like to do, is I graph one piece at a time, just like as an entire function, and then in pencil, and then I erase what doesn't exist. Okay, so we're gonna try an example now. Okay, so I give you a piecewise function, f of x equals 2x plus 1 for x is less than or equal to 1, and f of x equals 2 for x is greater than 1. And so it says sketch it, and so I'm going to try option 2 first. And so I'm going to just graph the function y equals 2x plus 1. Okay, I'm going to graph that first. So that is, my y-intercept is 1, and my slope is 2. Okay, if I were graphing 2x plus 1 alone, it would look like this nice purple line here. However, it doesn't exist when x is greater than 1. So we have to erase everything above 1, right? Because the function only exists at 1 and anything less than that. Okay, so I basically like need to cut off the graph at x equals 1. And since it's less than or equal to, we know that that function exists at 1, at x equals 1. So we have a closed dot there. Okay, so then the other function is y equals 2. And that is just the function that goes through, I'm going to do this in a different color, that just goes through y equals 2, right? So it just looks like that. However, it only exists when x is larger than 1. So I go to my x-axis and I say, oh, there's x equals 1. And so I erase everything before that, and then I just make my function from x equals 1 over to positive infinity. The problem is, if that's a closed dot, then it's no longer a function, right? And that's a greater than, so it doesn't exist there. So that's actually an open dot. And voila, there is my piecewise function. Okay, so then the next question says evaluate the following. And now this, you either want to have the graph and be able to visualize it, or you have to figure out where these things are happening and like what domain you're in and all this stuff. So I'll show you what I mean by that. So f of negative 2, right? That would be like taking f, the function, and plugging in negative 2, okay? So really what this is asking is, when x is negative 2, what's f of x equal to? Okay, and so you got to figure out which chunk of the graph you're actually on when x is negative 2. And so if you look at your bounds, right, when x is less than or equal to 1, which negative 2 is, in fact, less than or equal to negative 1, then you're using this first function. And so you can easily then just plug it in to that function, and you can say, okay, well, I'm going to be doing 2 times negative 2, right? You're plugging in negative 2 wherever x is, and that equals negative 3. And then you can actually see that on the graph as well. When x is negative 2, y is negative 3. F of x is negative 3. So go ahead, try the other 3 problems real quick, and then check your answers. And just note that the only one of these that was on the second chunk is D, because 2 is greater than 1. All right. Okay, I'm going to do this next example using the other way, so like using a table and just plotting points. So personally, the way I like to set up a table is I have the 3 different functions. So I have an x section of my table, I have my negative x plus 1, and then I have my 0, and then I have my x plus 1, so that I have all 3 different functions on the graph, or on my table. So then I pick some values of x. I'm going to go with some negative numbers. Really, you want the different areas of the domain. So I'm going to pick a couple negative numbers, so negative 2, negative 1, 0, 1, 2, 3. And I should be okay after that. I should be able to figure out what it looks like from there. So when you're plugging the x values in, you want to figure out what part of the domain you're on and what chunk of the graph you're on. So when x is negative 2, I need to figure out, am I here, or here, or here? Right? Negative 2 is, in fact, less than 0, so we are on the first function, right? So I just plug in negative 2 for negative x plus 1, right? Here's my first function, here's my second, here's my third. I'm just going to label them just so that you have those. And then I plug in negative 2, so negative 2 is positive 2 plus 1 is 3. So that's my first point on the graph. Now, the other 2 functions don't exist when x is negative 2. So doesn't exist, right? You're not doing anything with those functions right there. Same thing when x is negative 1. Also less than 0, so we're still on the first function. So negative 1 is positive 1, plus 1 is 2. The other 2 functions don't exist. So we don't do anything with those, okay? Then we move on to 0, when x is 0. Now, part of the definition of the function is that if x is 0, the function equals 0. So I'm in that scenario right now, because x is 0, therefore the function equals 0. So, oops, wrong section there, right? Because now this thing doesn't exist anymore, right? But the 0 function does exist. And then the last function doesn't, okay? Then I'm moving on to when x is positive, so x is greater than 0, in which case I'm on the last function. So the other 2 functions don't exist. Function 1, function 2 don't exist. When x equals 1, I have 1 plus 1, which is 2. When x is 2, my x is greater than 0, so I'm still on my last function. Then I have 2 plus 1, which is 3. Same thing with when x is 3. I have 3 plus 1, which is 4. And these other 2 functions don't exist at all. Okay, so then translating that to a graph, I just want to plot the points that I have. So I have negative 2, 3 is a point. Okay, negative 1, 2. And then that function, which is just a line, goes all the way to 0, but it does not equal that function at 0. So we have an open dot, and then we have that function, negative x plus 1. We have that function on the left side of the y-axis. Okay, when x is 0, y is 0. Okay, and that's the only place where that function exists. So it's just one little dot at 0. And then I have my new function, x plus 1, if x is greater than 0. So then I can just plot these points, 1, 2, 2, 3, 3, 4, and kind of connect the dots. And there you have your piecewise function. So if you're evaluating this function g of x, right, I'm going to label it g of x. If you're evaluating g of x at negative 1, you can either use the graph or you can use the function. I think it makes the most sense visually to see it on the graph, but at the same time, you still need to know how to do it algebraically. So I would just make sure that you understand, when x is -1, you're on the first graph because it's less than 0. -1 is less than 0. So you're plugging in -1 into this first function here, right? So it would be -1 plus 1. So that's 2. Again, you can see that on the graph too. When x is -1, y is +2. So then check your answers for the next two, and then that'll be it. All right, there you go. Bye-bye.